said that that was integrate over the all directions, I lambda cosine theta d omega in spherical coordinates. D omega is sine theta d theta d phi, which we're going over all directions. And its phi goes from 0 to 2 pi, theta goes from 0 to pi. If I lambda only depends on theta at most, then we can do the phi integral and just get 2 pi times the integral from 0 to pi I lambda cosine theta sine theta d theta, right? But then we say, okay, cosine theta is very important. So we just call that mu, because cosine theta is the cosine of that angle.
It's the projection of the.
Yeah, so it controls the projected area that we see, all that business. So we say mu is cosine theta, d mu is minus sine theta d theta. Change the limits, so mu of 0 on the bottom is 1, mu of pi on the top is minus 1. So then it becomes that f lambda is minus 2 pi times the integral from 1 to minus 1 of I lambda mu d mu, but then we say, ew, minus the integral from 1 to minus 1, why not just call it plus the integral from minus 1 to 1? That's what we were doing last time, and then we said that if I lambda is constant, so in other words, it's isotropic, it's the same in every direction, then f lambda is 0, because if I integrate mu d mu, that's half mu squared, and then when I plug in 1 and minus 1, it just cancels out and get 0. And physically, it's because there's, along any direction, there's just as much energy going into a solid angle upwards through the surface as is going into that same solid angle along that same line downwards through the surface. And what we're calculating here is the net flux, the difference between the outwards flux and the inwards flux, and it cancels for isotropic radiation.
Because the energy is.
Yeah, because basically, I'll put on one level, at any given wavelength, there's just as many photons going up through the surface as there are going down through the surface in any little narrow range of wavelengths. So there's no net energy flow, is what it comes down to.
And this is for a case, like you said, a narrow set of wavelengths, so like a d lambda corridor.
Yeah, because what we're calculating here is f lambda, and you have to multiply that by d lambda to find how much flux is in that narrow range of wavelengths from lambda to lambda plus d lambda.
So that integral, 2 pi integral negative 1 to 1 whole thing, times d lambda, and another integral would give us the full flux.
Yes, the full flux, right, the full flux is the integral of f lambda d lambda.
Okay.
Yes, absolutely, over all wavelengths. And for isotropic radiation, F and F lambda are both 0, because if F lambda is 0 at every wavelength, then the full flux is 0. And again, what that means physically is that there's just as much energy flowing up through any little patch I might draw in space as there is flowing down through that patch. So there's no net flux as a result of that. On the other hand, often we're interested in what is the outwards flux or what is the inwards flux separately. How much energy per second per square meter is going up through the surface, whichever direction through. And again, it can just be an imaginary surface hovering in space. How much is the flux upwards through it? How much is the flux downwards through it? And so that's what we'll do next, is compute what we call the outward flux.
I have one more question.
Sure.
So when you removed, when we take the integral of d phi, you said it's based on the assumption that the gradient flux doesn't depend on the azimuthal variation.
Right.
It's only depending on the polar angle.
Yeah, it's only depending on the polar angle, which is local. In other words, if we're looking at a surface, then if like a spherical star or whatever, then the polar angle is always away from the vertical to the local surface. And so So in other words, we define a coordinate system where the XY plane is the surface of the star locally, and the Z-axis is the normal to the surface locally. Mhm. Yep. And then we're assuming, to keep things simple, that the azimuthal angle doesn't matter anywhere. That all that matters is angle away from the vertical. Put another way, angle away from the line between you and the center of the star, essentially is what we're saying.
Okay.
Mm-hmm. Yep. So then the outwards flux is, we'll call it F lambda comma out. So that'll be only in outwards directions. So what range of theta is that? In other words, it's here to here and not below. We only want to consider energy which is flowing in the outwards direction. So this angle, what's the angle right now?
Pi over 2.
Zero. No, that's 0. And then at the horizontal,
Pi over 2.
parallel to the surface is pi over 2. So in other words, now we're going to integrate, if we do it in spherical coordinates, it's going to be 2 pi times the integral from theta equals 0 to pi over 2 I lambda cos theta sine theta d theta. And when we do the substitution, now this time, we've got again, mu of 0 is equal to 1, but for pi over 2, mu of pi over 2 is equal to 0, so our integral goes from 0 to 1 instead of minus 1 to 1 this time. So we've got 2 pi integral from 0 to 1 of I lambda mu to mu in this case. And if I lambda is constant, at least over the outward hemisphere, because we don't care what it is down there. So we only care that it's constant in outward directions. Then what we'll get is f lambda out will be 2 pi I lambda, because I lambda is constant, pull it out of the integral from 0 to 1 of mu d mu, but the integral of mu d mu is half mu squared, so then we'll plug in 1 and 0, which will give us 1/2 minus 1. If we plug that in, so we just get pi times I lambda. Yes?
You start with 0, 1 to 0, but the limits and the rest are 0 to 1.
So here it's 1 to 0. Oh, wait. Yeah. From 0 to pi over 2, and then cosine of 0 is 1, and cosine of pi over 2 is 0. So you're saying where's the minus sign, right? Is that what you're saying?
No, I was asking how did the limits get reversed?
Yeah, that's right. I know. That's exactly what I'm thinking is right. Is let's see. Let me think here. On some level, I mean, it's got to be positive, but yeah. Well, let's see. What did I?
All to the minus.
What's that?
All to the minus.
Yeah, I know. It's because I mean the outward flux can't be negative, right? I mean it's well, I'm sorry. It could be that all the radiation was flowing downwards, but we want there is radiation flowing upwards from below, so we don't want this to end up being negative.
Is there an integral identity where you can reverse
No, I mean,
the limits using a minus sign?
well, certainly it's true that the integral from a to b of f of x dx is equal to minus the integral from b to a of f of x dx. That's always true, and that's what we were using over there. That f lambda would be minus 2 pi times the integral from 1 to minus 1 of I lambda mu du mu, and then we just said, oh, well, I can change the sign and flip the limits and the integral stays the same. And we were good to go. And so here, what's going on here? We definitely want to go from 0 to pi over 2, and that is cosine of 0 is 1. Okay, what's going on here? Oh, I know what it is. This would have had the minus sign because sine theta d theta is minus mu du mu. So I should have had a minus sign right here.
Oh.
This should have had a minus sign because that is, that is minus d mu, right? Because mu is cos theta, so sine theta d theta is minus d mu. So it should have started with, I could have gone, in other words, the immediate step is this is minus 2 pi integral from 1 to 0.
And then
and now,
and then you reverse it.
then I reverse the limits.
Oh.
Yes. Okay, so now I'm happy. Yes, thank you for pointing that out. So in other words, I was right to write that down, but in a sense I skipped a step, which confused both of us, is what it came down to. And then plug in isotropic radiation, or at least isotropic in the outward directions, constant over the outward directions. You do the integral and you get that the integral is just 1/2, so you get pi I lambda. And now I will remind you that long ago we had found that F lambda was pi times B lambda for blackbody radiation. Blackbody radiation is isotropic, so that's a special case of this. In other words,
So this is like more general.
this is more general, yeah. If the radiation is isotropic, then the outward flux is pi times the specific intensity. So remember that before we found F lambda equals pi times B lambda for blackbody radiation. And that's a special case of this relation. And before we just called it F lambda because what we meant was the outward flux from the surface of the black body. So strictly speaking, it might have been better to call it F lambda sub lambda out. Because blackbody radiation is isotropic. But now we see that it's more general than that. If the radiation is isotropic, then F lambda in the outward direction is pi times I lambda. Okay, so now, because we multiplied I lambda by 1 power of mu equals cosine theta, we call the flux the first moment, we say, of the radiation field. It's just terminology. The first moment of the radiation field is what you get when you multiply by 1 power of mu equals cosine theta. Because we multiplied by 1 power of mu, multiplied I lambda by, I should say, the first power. Mu equals cosine theta. We say that F lambda, not F lambda out here, but just F lambda, in other words, integrating over all directions, is the first moment of the radiation field I lambda. And again, it's just a name. Moment doesn't mean like moment of time here or anything like that.
Oh, it's just like.
It's just a word. It's just a word. Really. Because then we're going to talk about the second moment being what you get when you multiply by mu squared and integrate over all functions.
How many such moments are there?
It's an arbitrary number, but you can have the nth moment, but only a few of them are physically interesting, is what it comes down to. Okay, the 0th moment, I don't know, I guess I don't need that E there, I'm not even sure. So, kind of as an aside, the 0th moment would be the mean intensity. Remember, I lambda was 1 over 4 pi, and then we just integrated I lambda d omega, so there was no cos theta that was multiplied before in between the I lambda and the d omega. So that's the 0th moment. The mean intensity is the 0th moment. The flux is the first moment.
Because it's multiplied.
Because then the flux was I lambda cos theta d omega that we integrated. So now we're going to show that the second moment is related to the radiation pressure. So the first moment is related to the net flow of energy. The 0th moment is related to just the average intensity. And the second moment is directly related to the pressure exerted by the radiation field. And we're not going to do the third moment because we're not going to use it, is what it comes down to. Or the 4th, or the 90th, or anything like that. But we will use the 507th. No, kidding. Now we show that the second moment which will be integral minus 1 to 1 because we're going over the whole sphere, I lambda mu squared du is related to the radiation pressure. So we're used to thinking of gas pressure when we think of pressure, but in a star, the radiation also exerts pressure. And sometimes the gas pressure is much more important than the radiation pressure, but sometimes the radiation pressure can in fact dominate. In fact, later we'll see that the maximum possible mass of a star is set by the fact that if you had a main sequence star that was massive enough, its luminosity would be so large that radiation pressure would exceed the force of gravity in the star's outer layers and blow them off of the star until it got down to what's called the Eddington limit, the maximum mass such that the star is not so luminous that radiation pressure blows its outer layers off into space.
Okay, so it's like the limit just before the supernova.
No, it's actually not before the supernova. It's how, so here we're talking about when the star's on the main sequence, okay? Suppose this really massive cloud collapsed to form a star that was 250 times the mass of the sun, okay? In order to pull that off, the core has to generate enough pressure to support the weight of the overlying layers. And that's the physical basis of the mass luminosity relation on the main sequence, that the more massive a star is, the more luminous the core has to be. The nuclear reactions have to go faster in order for it to be hot enough to have enough pressure to not have it crushed under the weight of all the layers above it. And so what we find is that luminosity rises a lot faster than mass does. It goes like about mass to the 2.5 power, or 3.5 power, 3.5 power, right? And so the balance between pressure and gravity in the star is not just gas pressure and gravity, it's total pressure, radiation pressure plus gas pressure. And the idea is that as you make the star more, as you make a star more and more massive and yet still have fusing hydrogen in its core, the radiation pressure becomes more and more important in the outer layers compared to the gas pressure, just because there's so freaking many photons there because it's so luminous. And when you hit the Eddington limit, then the radiation pressure alone is equal to the gravitational force on a thin layer at the surface, if you were to consider that. And so essentially that would be saying you don't need any gas pressure to support that outermost part of the star at that point. If you go any larger, if you add any more mass, now the radiation pressure at the surface by itself is stronger than the force of gravity. A little parcel of gas will have a higher outwards force due to radiation pressure on it than the rest of the star pulling inwards on it due to gravity. So even with zero gas pressure, you cannot have gravity be counteracted. I mean, you basically have a situation, even if you didn't have any gas pressure, which you will have some, there's a bigger outwards force than an inwards force on the star's outer layers, and so they blow off into space as a result of that. So it wouldn't be stable. A star 250 times the mass of the sun would rapidly lose mass from its outer layers because it's so bright to support the inner layers that the outer layers are blown off into space. It'll lose mass until it gets down to the Eddington limit, the stable configuration. And there's various estimates for that, but it ain't 250 times the mass of the sun. It's thought to be something like 85 times the mass of the sun. We have seen stars more massive than that, but they also have very strong stellar winds, so they probably are in the process of getting down to the Eddington limit, basically. So all that's a presage. All that is to say radiation pressure is actually important.
And I think you mentioned like during the summer that more massive stars have their outermost layers radiation zones.
They do, yeah, and that's not directly related to this.
Okay.
We'll talk about that when we talk about convection and the conditions under which convection happens versus doesn't happen. Yeah. Basically, we'll talk about the conditions under which if I had a bubble, if you will, of gas, a parcel of gas within the star, and for whatever reason it became a little less dense than its surroundings, and as a result became buoyant and started to rise. The condition that it will keep rising is that it stays warmer than its surroundings as it rises, because then it will always be less dense than the surroundings, and it will therefore always be buoyant. But we'll find that, and then what we'll find is in a radiative zone within a star, a bubble that started rising, its temperature would fall faster than the temperature outside of it was falling. so that it would actually quickly become denser than its surroundings and sink back down again.
I see.
So we'll get to that in tremendous detail later on. Right? But for now, we just want to talk about the radiation pressure. So what I'm going to draw is a picture to start with of a perfectly reflecting surface. In other words, let's imagine a mirror that is perfectly reflecting. It never met a photon that it couldn't reflect. Real mirrors can come pretty close to that, but we're going to make a super duper mirror that really does reflect all the light that falls on it. So what we'll do is we will draw a perfectly reflecting surface. And here's a little piece of it of area dA. And it'll obey the law of reflection if it's a nice, smooth, perfectly reflecting surface. In other words, if a photon comes in at some angle to the vertical, it reflects at exactly that same angle to the vertical. So, as usual, we'll make the z-axis be what we'll call the z-axis the vertical direction. So, I will draw here two solid angle cones with dashed lines to mark their centers. And so they both make the same angle theta with the z-axis. And the idea is that if I drew this perfectly, here is radiation heading towards the surface from some solid angle cone d omega on one side. So I'll draw an arrow there to say radiation is coming in from that cone onto the surface. And if every photon obeys the law of reflection, we'll make an identical reflected cone on the other side. So there will be the same size d omega of reflected radiation on the other side. My drawing sucks, so I'm trying to make it a little better. But if I'm really drawing this well, I just want to say, in my notes, I was very careful to draw it beautifully, and then I try to do it on the board, and it's like, no. So, try to make it look like the other cone did. Those cones are supposed to look just like one another, just the reflected versions of one another. And so that one's also d omega with radiation going out from that. And so we'll consider a photon coming in, and the relation between momentum and energy for a photon is that E equals PC. Do you remember that relation for photons?
Or, yeah,
that's
momentum
right.
times the speed of
Right, yeah, the energy of a photon is its momentum times the speed of light. It comes from the general relation for particles is E squared equals mc squared squared plus PC squared, but photons are massless, and so you just get E equals PC for photons.
I remember this from 280.
Yep, good, excellent. So for a photon with momentum, P equals E divided by C. It's energy divided by the speed of light. The change in the Z component of the momentum is, we'll call that delta PZ. That'll be the final Z momentum, so we'll call it P sub Z comma F, the final Z momentum, minus the initial Z momentum, d sub z comma I. The z component is the total momentum times cosine theta, because we're projecting the vector onto the z-axis. So that will be,
Oh, to calculate the change in
yeah.
momentum. Z component.
So we've got e cosine theta over c. It's got positive z momentum after reflection. Its initial momentum in the z direction was negative,
So,
right?
yeah.
So we get minus e cos theta over c. And this works with a basketball or a BB reflecting off the wall too. The same principles involved here. So that's equal to 2 e cos theta over c. The change in the momentum is twice the momentum in the z direction because of the fact that it comes in negative and goes out positive. Yep.
So the net is double.
So the net's double. Yep. So then we say, okay. Have you got that written down yet? Or I'm happy to wait for you to get it finished. Yeah. Because I always got to catch up to you, so I have to remember that. So now we say, okay, that's one photon. There's lots of photons doing it. Let's put this in terms of specific intensity. If dE lambda is, well, from the definition of specific intensity, that's I lambda, d lambda, dt, dA cos theta, d omega, because I lambda was defined to be dE lambda over all that other stuff.
Yeah.
Right? So take it to this side. dE lambda is I lambda times all those little differentials. So I'll just say is the energy arriving from solid angle d omega, etc. In other words, in wavelength range d lambda, in time dt, but I don't want to write all that, so I'll just say etc. means all that other stuff. Okay? Then what we should say then is, in terms of the momentum, dp lambda is 2 dE lambda cos theta over c. In other words, for one photon, it's 2 e cos theta over c. So for lots of photons, it'll be 2 dE lambda cos theta over c.
For any one photon.
Yeah, well, for any one photon, that's true.
Okay.
For any one photon, that's true. So then what I'm saying, well, this dE lambda is due to lots and lots of photons that are coming from solid angle d omega in time dt in wavelength range d lambda onto the surface dA at angle theta from the vertical, right? All saying all that, etc. I'm saying, since it works for each photon, collectively it works for the radiation coming from that solid angle.
Yeah.
Okay, that's the idea there. So that means that we can say that it's 2 over c times, and then write out what the dE lambda was. I lambda, d lambda, dt, dA cos theta squared d omega, because the E lambda already has a cosine theta in it. The dE lambda does. So dE lambda cosine theta has 2 powers of cosine theta. Because we're multiplying by the dE lambda cosine theta. That projection, in other words, of the momentum component is also showing up here. here.
You have the second momentum.
So that's why we're getting the second moment. One moment is from the way we define specific intensity to involve the projected area. The second one is because we're looking only at the z component of the momentum, and that involves a factor of cosine theta. So I'll add where it is understood that we're discussing the component of momentum normal to the surface. The component of the momentum along the surface isn't affected because the motion parallel to the surface isn't changed. It's only the vertical motion that gets reflected. Same deal. If I bounce a ball off the wall and I ignore gravity, only the y component or only the z component of the motion changes. Its shadow along the surface would just keep moving at the same speed in the same direction. So where it is understood that we're discussing the component of momentum normal to the surface. Now we're trying to turn this into the pressure, and with gas pressure, the gas pressure on the door is due to molecules bouncing off of it. The molecule comes in, bounces off of it. So if the momentum of the molecule changes by twice the amount of the incoming momentum, where did it get that momentum? It got it from the force that the door applied on it during the collision, right? And so momentum conservation is saying that whatever momentum the door transfers to the molecule transfers equal and opposite momentum to the door because the total momentum has to stay the same. That's true for the light as well. In other words, the momentum of the light is changing upon reflection from this mirror. And because light is carrying momentum, that means that the mirror must be transferring momentum to the light, but that means the light has to be transferring equal and opposite momentum to the mirror, or in other words, it must be exerting a force on the mirror, because momentum is, the rate of change of momentum is the force. That's a force.
Yeah.
And so that's why radiation exerts the pressure, is because it carries momentum. So if it reflects off this surface, it must be giving momentum to that surface because the light's momentum is changing and momentum is conserved. And so therefore, the momentum of the surface has to change in an equal and opposite way. And now, of course, the mirror could be attached to the surface of the Earth, and then that gets transferred to the entire Earth, and you're not going to notice it, right? Giving a little momentum to the Earth only slightly would change its motion. But you know, actually, the light from the sun is exerting pressure on the Earth, which partly counteracts the sun's gravity. It's way, if you count